right now exactly what you need to know for that test. I know sometimes we got to go back and review. And here's one thing I'll say. Whose calculator is this that got left up at the front? One thing I will say is, at the front? You got one right there. Did you put yours up on the whiteboard? So please find the calculator that you logged into. I'll say you should have logged in because that was the first part of the bell ringer. But make sure you have your calculator. Do y'all know how to look to see if you have the calculator you logged into or not? Not just that. So if you go to the little circular arrow thing at the top, it'll tell you who's logged into that calculator. So Kyron Davis is logged into this calculator, okay? So to study for that test tomorrow, remember, we've been working on this stuff. You've got your check your understanding questions. By the way, like one thing I want to remind you of and I want to emphasize is this. When you get to college, which from the talks with most of us, you don't need to go to college, but from the talks with most of us are planning on going to college. There are some classes in college where they're going to give you homework assignments and you have to do them for a grade. But when you get to upper level stuff, those homework assignments are not going to be mandatory. What's going to be checked is your assessments. Or at least the vast majority of your class is going to be your assessments. When I'm walking around and I see none of the check your understanding questions done, that means we have not been studying over time. Learning takes time. And that's why with the bell ringers every day, what do I give you a chance to do with your bell ringers? Well, ask questions based on the check your understandings, right? I've given you the solutions. Listen, I know that homework traditionally is one of those things that we get a grade for, but the reason why I don't do a grade for check your understanding is because check your understandings, homework assignments, really need to be learning situations. They need to be a chance for you to make mistakes and for you to grow as a student. But if you're not doing them, can you make the mistakes to grow as a student?
No.
Okay, if we're struggling, I need you to start doing those check your understanding questions. I know we're 3/4 or over 3/4 of the way through the class. Let's finish the last quarter of the class really strong though. Do those check your understanding questions. It's going to help you prepare for college better. I got to figure out a way to communicate that better to students and communicate that to parents in the future, but your learning matters, and that's why I don't grade you on it. That's the learning time, not anything else. Okay, all that being said, we should be logged on to our calculators. What we are looking at is we're starting this unit on inverse functions, and so our agenda, we've done the review, we're on lesson 3, transforming nonlinear data and developing models, and so this lesson is going to be the core of everything that we do with this unit, okay? That first lesson is always the introduction. Remember, what was the very first lesson we did with Unit 5 on higher degree polynomials? Anyone remember? Huh? It was about the degree. Remember how we had the white books up and we did that mathematic activity where we looked around the room and we looked at, okay, as the degree changes, how is that changing the number of extrema, the number of x-intercepts? Guys, that was the very first thing we did because it's the foundation. I need y'all to make sure that you're doing this foundation. All right. As a quick reminder, what's a one-to-one function? Actually, let me do this. One input maps to one output. Okay. Is there anything else that's necessary for a one-to-one function? Okay. So I'll say this. Only one of these functions up here is a one-to-one. Which one? Why the second one? I mean, one input maps to one output and f of x too, right? Okay, so here, that output of 4 has how many different inputs? 2. So that would not be a one-to-one function. Is it a function? Yeah, definitely a function. Is it one-to-one? No. So remember, when we talk about one-to-one, graphically, it has to pass both the what? Horizontal and vertical line test, okay? So notice, and these are just made up examples there, but you don't necessarily go with those tables. So one-to-one, each input maps to one output, and each output is mapped from one input, not one-to-one. Still a function, but not a one-to-one function. So we want to keep that in mind there. All right. So remember, the whole thing with this unit is, yes, we're trying to understand what type of functions again? Anyone remember? Hey, look at that proficiency scale for Unit 6. What was the name of it? There we go, inverse functions, right? We're trying to learn about inverse functions, but we're doing it within context, within data. By the way, Xander, you need a copy of this. My bad, dude. Anyone else not here yesterday and need a copy? Xander, I'm going to have to find it in a minute. This is what happens when you start printing out things for other classes. I'll find it for you when we go start working on the next bit. Here's at least, yeah, here's the proficiency scale. I'll have to look for the lesson though in a second. Okay, we're doing this all inside of context, okay? I'm going to skip that. So remember, here's that proficiency scale. In the foundation piece, have we covered or talked about all those different things within the foundation of that proficiency scale? Miles says he thinks so. Drake, what do you think? Have we covered everything inside that foundation at some point? You think so? Is there anything you're unfamiliar with? Go for it, Miles. Ah, great question. So index of a radical. I was hoping someone would bring that up. So what's the index here? 3. What's the index here?
2.
And the index here?
7.
So remember, it's just what type of root it is. It's what's inside that little crook there, right? It's what type of root it is. All those other things, radicands, radicals, powers, exponents, we've done those things. Features of functions. By the way, what features could I be referring to when I say features of functions? In behavior. Domain. What'd you say? Number of extrema, range, all those things, x-intercepts, y-intercepts, those are the features of a function that we'll be wanting to analyze. But this is what we're getting into. This is all of the stuff. The lesson that we are looking at today is really focusing right here on this concept. We will use the next couple of lessons to get to these concepts here. We'll do a little bit with one-to-one. But we're really going to be focusing on this word here, or this term, inverse of functions, invertible next lesson. One-to-one function, and we'll talk a little bit about radical functions later. But those are the focal points. These two things right here are the foundation for this entire unit, okay? So we got to make sure we get these down. And so yesterday, I'm going to go ahead and pull up the Inspire file. So remember, lesson 3, not lesson 2. Is what we want out right now. Didn't I pass? I passed lesson 3 out yesterday, right? It says. Say it one more time.
Is it task 2?
No, lesson 3. It looks like this at the beginning. Yeah, task 2 is that concrete stuff. That's why it's a part of the bell ringers. I would say it should be in there. And Xander, I'm the worst. I will find a copy of it or print it out, one of the two. No, see, that's not the option.
So you want to get task?
I want you to get lesson 3 out. See, I found it. Task 1 is what we're looking at right now. Okay. Okay, technology piece. So, as a quick recap of where we got yesterday, because it's going to help you work today, we got to 1.2, and this is a made-up artificial situation. When we looked at height here, was height a linear set or a linear function? Why do we know that that's quadratic right there with the height? Ah, remember, we looked at that. Rate of change. When we're talking about tables, rate of change is a great option. Constant additive here, so my rate of change is linear additive. Taylor, can you please let Marianne So linear additive rate of change is right there. And so it's what type of function? Quadratic, right? X to the first, x to the second, quadratic function. Woo! But that's not linear. Linear is not helpful. It's not super easy to work with. So what did we do to that height to make it linear? Right, so remember we went to this top box here. So I need y'all to be on 1.2. I need y'all to go back through this really quickly to remember how we did this to set us up for today. So linear in that gray box. So where it says equals, yeah, we hit the equal button. Remember there's that equal button underneath the word control. If I can get mine, there it is. Equals square root. So control and then squared, right? So we should see that square root symbol. So remember, you need to go to the linear one. Hit escape. Just hit escape. There you go. There you go. You need to be underneath linear while you're doing this. And then, how did I get the variable height into that square root symbol? Yeah, that's right so far. So I click variable. Remember, there's that VAR right above the number 9. So number 9's here, VAR's here. And what am I taking the square root of? Taking the square root of height. So that's what we should see at this point.
Oh.
So VAR, above the number 9. So help a friend out if they're not seeing it. Make sure you're looking out. Height. You're trying to do linear, dog. There we go. Now hit enter. Okay. So we should see, literally, how did this number 1 get here? Like, why is this a 1 right here? Yes, Shadidra.
I lost it, but
Okay, I'm going to come check on you in just a second. Okay. Once I get us going on the next piece. So why is this 1 right here? What did the calculator do? So I should have brought this up. It did the what? Square root of what? Of 1. What's the square root of 4? What's the square root of 9? Square root of 16. So the calculator's just taking that square root for me. It's making my life easy, okay? And is it now linear? Yes. All right, we go to 1.3. Remember, we didn't see our data. Why did we not see our data there? So remember, it's not graphed, okay? So keep this in mind, and the instructions are on here, but how do I graph the data when the data is not already graphed? Go to menu, because that's the fun thing that lets us do cool crap. What else do we go? Oh, no, sorry. One thing I forgot to remind you of. If you're not clicked on the graph, it's not going to give you that option. I'm actually clicked on the left part here that has instructions. I'm going to click on the graph, and you should see a blue border once you click on the graph. Now what do I do? Menu, then graph entry, and the type of graph is a scatter plot. Okay. And if you're not 100% there, when we break in a second to start talking, come meet me in the middle and I'll help you get caught up graphically here. So I'm going to go to scatter plot, and what's going to be x? So I'm going to go to variable. What's it going to be? X stat, right? Like literally, x is my x stat, and what's y going to be? Height? I would say we tried to linearize that data, right? And I'm going to hit enter. And is that data now linear? Yeah, right? So not only was it linear in that table, it was linear in this graph as well. And so this is what the last lesson was about, is learning how to manipulate this line to fit that data. And now it's not perfect, but it's pretty darn close. Notice my slope is really close to 1, which wasn't it constantly adding by 1. And then my y-intercept was 0, and so that's pretty close to what I got. Now, yes, bless you. Here's the context, okay? So again, here's the context that we're getting into at this point. So remember, that's a recap. You got 3 people in your group to help support you. I need y'all to pause on that. I need us to go to activity 2.1, okay? So, activity 2.1. So problem 2 presents data that is non-linear. A fun fact about car crashes, and I don't know if this would be a really fun fact, but when you're trying to stop, because hopefully you're not trying to get into a car crash, right? What happens on the road when you try to stop? Or maybe you've seen other people do it? but what happens to the road a lot of times in that case? The scuff marks, those are called the tire tracks or the skid marks, right? So there's skid marks, right? Police officers use things like how much damage was done to a car. They use skid marks to determine, hey, how fast was that car driving? And the way they do that is they've actually used data that's been collected. If you're driving faster, what's going to happen with those skid marks?
They're not gonna be as long.
Wait, if you're driving faster?
Oh, I thought
I would say the faster you drive, the longer those skid marks get, right? And so there's data collected on different cars based on their weights, things like that, of how long the skid marks are going to be based on how fast someone is driving. And so the fact of the matter is, it's really hard to create a model by hand when it's nonlinear. You know how we just kind of move that line around a little bit? Can't easily do that with a quadratic, or a cubic, or a quartic, or a quintic, or anything else, okay? There's lots of other things out there. And so what we have here is nonlinear data. As the speed increases, what's happening to my stopping distance? It increases. Does it increase at a linear rate though? Or does it increase at a constant rate, I should say? No, it's like plus 46, that's almost plus 80, that's almost plus 100, right? So it's changing how much it's increasing by. And so when we graph this data, it's going to be hard to make it linear, or it's going to be hard to create a model for it. So what are we going to do to that data? We're going to linearize it. We're going to try to make a linear set of data. Now, here's what I want to point out. Why did we take a square root in that last question? Because it was quadratic, and a square root is the, let's reword that language. Inverse. Remember, opposite of 3 is only negative 3, right? Opposite is only the opposite sign. So when we are talking about these things, remember this is inverse functions, we're talking about inverses. So we took a square root because it was quadratic, right? Peyton, you with me? You sure?
Yep.
I'm already boring you this much? Okay, just make sure. Okay, so let's just think hypothetically, what if it was a x to the 4th, a quartic? What do you think we would do in that case? Would we take a square root again? It'd be a which root? A 4th root, right? We'd apply the inverse. If it's a cubic, what are we going to take? The 3rd root, okay? Now, what I need you to do is, as we're looking here, first I want you to talk as a group, what are the independent, dependent variables, and then I want you to apply some operations to that dependent variable to make it linear. Notice, and I just want to point this out, if I hit equals and I do stopping distance, and I'm just going to do something crazy, like I'm going to square it. Does that make these things linear?
No.
Not at all, right? That's like plus 6,000, or no, yeah, 6,000. Then it's going up to 25,000, so that's what, 17,000-ish? That's not linear. That's not what I want. What do I want this set of data to become? Linear. So I want you to talk within your groups. Now I do want to remind you, the previous question, perfectly linear. But the real world, is the real world perfect or is it a little messy? A little messy. So it may not look perfectly linear, but that's okay. We want it to be close to linear, okay? So first, work with each other. And by the way, let's do this at vertical surfaces, right? Writing answers around the room so I can hear your conversations. I can support you. And with that, I want you to first do that question about what are the independent, dependent variables. And then I want you to work together to linearize that data. Come up with some predictions about what you think might linearize it, and just try it out. You may get it wrong first, and that's okay. Test out a few operations to see if you can get it linearized. What are your questions before we go to vertical surfaces? I want to pause y'all really quickly, because I think one of the issues is that we're wanting this to be perfect, okay? But remember, Kyron, is the real world perfect?
No.
No, what is it? It's a little bit messy, okay? Hey guys, I need y'all to come over here real quick. I want y'all to look at this, because some of us started here, and we didn't finish, but no, hope that's not over here. Come on. Okay? Now, I want y'all to look at this really quickly. So, this group, which several of us did this, right? Remember, so I saw 3 groups. Well, this group was working on it earlier. We said earlier, if it's quadratic, then we took what root? Square root, right? And what can tell us if it's quadratic or not? The rate of change, right? Now, here is the first set of differences. They worked on that. And then Elizabeth was like, this isn't good. She tried to keep going. I think someone else said that they tried to keep going. But look, this right here is 25.9. That's how much we're adding. This is 23.9. That's how much we're adding. This is 23.5. Now, are those exactly the same?
No.
No, because the real world is what?
Messy.
But could that be close to constant additive? Okay, so constant additive here. So constant additive, which would make this rate of change linear additive, making the stopping distance quadratic. So did any of us take a square root earlier? Miles, you did? Okay, so I need you all to come up over here really quickly. But it's still on your calculator, isn't it? Okay, so I don't need it written down, because remember, I can pull up your calculator. Let's see here, Miles Johnson, there we go. Capture, selected handheld. Oh, that's not what I wanted. I lied. I want to make you the presenter. Connection error. Did you take the top off your calculator? There's some issue. All right. Does anyone have the square root in their calculator right now?
I do.
Elizabeth?
Somebody factors.
Okay, so let's see. Elizabeth. It's not in order. Why not? There we go. Okay, so make presenter. All right, so look in here. Stop, square root of the stopping distance. So if I check it, this is plus 2.9. And notice I'm just estimating. These are not perfect. Tell me, when we took the square root, is that pretty constant additive?
No.
Is it perfect? Because the real world is messy. So, did the square root linearize that set of data? 100%. Now, I need everyone to have that in their calculator, because in a second, what I need you to do, Elizabeth, can you go to 2.3 for me real quick on your calculator?
Yes.
Thank you. So, notice there's no data here. That's not super helpful, right? But how can I get my data on this graph? So remember, hey, pause for a second. I need to make sure you follow this along so you can do this. So, what are you going to press? All right, menu, let's do cool crap. I want my data, so where am I going to go? Graph entry / edit, then scatter plot. And what do I want to make my x variable? Was speed my independent variable, my x?
Yes.
Okay, cool, so let's put speed in there. What do I want to make my dependent? Now, was the stopping distance linear? No, I'm going to put in linearize. I'll show stopping distance in a second, but put linearize, hit enter. Now pause again, because I need y'all to pay attention. Can I see this linearized set of data very well?
No.
I don't see nothing. So what do we need to do? Menu and zoom data. So remember, we have this option for zoom data. I'll take care of it in a second, don't worry about it. Did you do zoom data? Number 4? And then number 9, zoom data. Can we see our data now pretty well? Hey guys, I need y'all to look at that data. What does that data look like? That looks like a line. I need you to develop a model for that linear set of data. So just like how we did last lesson, manipulate that line to find a linear model for that data. Okay, so 1, remember, you got a group, work with each other, you have to linearize the data before you can see it. No, you didn't.
Oh, that part.
Yeah, you got to linearize that data. Remember, take the square root of that stopping distance.
Mr. Candy, it won't rotate.
It will.
You won't, you can't rotate.
Yeah. It is rotating. So notice the y-intercept staying the same, so it's rotating. You might now need to go back in and change your y-intercept and things like that. Okay?
Thanks.
Yep. Yes, Deidre. Alright, never mind. Okay, so one thing I would need to caution, excuse me, hey, Landon, I'm teaching, bro. All right, one thing I want to caution really quickly is there's some of us who the stuff was not graphing. If you accidentally delete that header of linearize, then the graph does not have an independent and a dependent variable, so it cannot graph it, okay? That's why some of y'all are having trouble graphing. Make sure that stays there. All right? Nope, not what I want. So what we have for a lot of us is a linear model. Now, I need to caution you. You know what every single person forgot?
No. You know what I'm
Where everybody?
I am going to tell you.
Okay.
So, one,
Whoa.
we got some... Jaden, go to 2.2 for me real quick. No. Go to 2.2 for me. Hold on, go to 2.2. Hit escape. Jaden.
Oh, I didn't say that.
Because I want y'all, so Jaden, go back to 2.3. This is actually a really good mistake that I want us to learn from. So 2.3, guys, look at the shape of this graph. Does that look linear? Maybe exponential, maybe, see, I wouldn't have said exponential. I might have said quadratic, because what type of function do we decide it was? Quadratic, right? So make sure you linearize that data. You just put stopping distance in there. But I am glad that I accidentally picked on that one to learn from it. So let's look at crystallines. All right? So crystallines is right here. Looks nice and linear. Maybe we can get a better model, but I ain't sweating it a ton.
You should click on Hope.
You should look at mine.
Yeah, you should click on Hope.
I think you should.
Why Hope?
Because hers
Just
better
look
than
at it.
Like it's
Look
crushing
at
it?
Yeah, it's crushing it.
All right, let's see. Hope.
Shush.
Why y'all doing that to each other like that? What do y'all think? Does that look pretty good?
Look at that.
Oh, wow.
That looks
That's
pretty
pretty
good.
close to all those points, right?
That look like mine. Oh, never mind.
All right.
Yeah, no.
So yeah, I mean, I like this, but guys, here's the thing. I need y'all to remember this. This model. Are we actually saying that the linearized data is perfectly hitting all those points?
No.
So what did y'all forget? There's a cute little something.
What the heck?
Oh, the cute little hat!
It's
Guys.
not cute.
It's not cute, but it's a hat.
I think it's cute. All right, so it's a hat. So first things first, why do we want this hat? Why do we need this hat?
Doesn't it show like it's a
Prediction.
estimate? Oh,
It's an estimate. It's a prediction. Guys, if we don't have that hat, we don't actually have a model. We're saying that that is the function. So we want the hat. Oh, did y'all have the hat originally?
Yeah.
I'm proud of y'all. Did you? Are you lying to
No,
me?
I didn't.
Okay.
I promise.
I don't remember seeing the hat over there. All right. So here's the other thing, though. I want y'all to keep this in mind. What are we actually predicting?
The speed and stop this.
Well, which one are we predicting?
All the stop this.
But do we actually have? But hold up. Look again. Do we actually have the stopping distance for this model?
Nah.
No.
We definitely don't.
We predicting.
No.
We're predicting the what?
The linear.
The linear.
Remember, this is the output, right?
Y'all know what I'm trying to say.
The predicted linearized stopping distance, if you want to add that in, you can. But the predicted linearized stopping distance is equal to, based on this, 0.33, what is x representing?
The
Speed.
Yeah, I knew
Okay. Now, I want to point this out, okay? This is how I would write my model from the beginning, because this is actually what we are representing. Please, in a second, when you write down your model on page 2, right, because it asks for, so 1, by the way, what, when we look at the question about, sorry, when we look at this question, so when we look here, what transformation or what operation linearized our data? What was the transformation that linearized that data best? What transformation linearized that data best? Which one did we use? No, what transformation? What did we do to the stopping distance to make it linear? Square root, thank you. We took a square root. Please make a note to yourself here. Why did we think that a square root transformed or linearized that data best? Because we noticed, hey, that's a quadratic function. So notice when we looked at Jaden's graph, right? Did it have a parabola shape, a quadratic shape? Yes. When we looked at the rate of change, what type of rate of change did it have? What type of rate of change did it have? Linear additive rate of change. Thank you. Y'all give me heart attacks. Okay. So we took a square root because we thought it was a quadratic function. Make sure you have a note about that. Okay. We thought it was quadratic, so we took a square root. The next thing I do want to point out is, how did we know that that square root transformed or linearized our data pretty well? There's two things we saw. So when we took the square root, did our data look pretty close to constant additive? That's one piece of evidence. How else did we know that we transformed and linearized that data pretty well? The graph was pretty what? Linear, right? They're all telling the same story. So guys, please make a note of why we picked the operation that we did and how we knew that the data was roughly linear. So make a note about what we did to linearize that data and how we knew that it was roughly linear. Okay. So guys, I need to cover one more thing really quickly in a second, so I need you to get this information down so I can cover this last detail. And once again, when I record my model here, I'm going to put my variables at play because I'm not just talking about X and Y, I'm talking about linearized data, I'm talking about speed. That's me personally. And that's because it's based off of sound statistics and mathematics principles. It's not me just making stuff up, I should say that. Okay? So record your model. Make sure you have that reasoning in there. And guys, for those of us who don't have anything under that second paragraph, like again, you need to have a note to yourself about how we chose the square root, how we knew it linearized the data. So guys, please do remember, I do record, so for those of us, I gotta get this next little piece down. If you did not get something under that second paragraph, please go watch the end of this video, but I gotta cover this because I need you to pay attention to this detail. So, it is important to note that the above model is only for which set of data? Linearized. But what I really want is for the original data. I want a model for the original data, and we can find that really easily. So, with such models, it is appropriate to write equations with the transformation algebraically applied to the dependent variable. So instead of saying y hat, what did I do to all my y values? What did I do to the stopping distance? I took the square root of it, right? So it's most appropriate to say that the square root of y hat is equal to this. It is most appropriate to say that the square root of y hat. Now I'm making my y hat the stopping distance, which is going to be useful in a second. But the square root of y hat is equal to that set of values. So if the square root of y hat is equal to this, what do you think y hat might be? How would I figure out what y hat is? What is the opposite of square root? And be careful, not opposite. Inverse of square root. What's the inverse of a square root? Say it louder, Elizabeth. A square, right? So how would I get, so I need to square this, right? Can I just square the left-hand side? Should I square the other side? Now notice, I'm going to square the entire thing. And I've got to do this quickly. But I just want to show you something before that bell rings. We're gonna pick back up with this on Thursday, because what do you have tomorrow? A test while I'm out, but watch this. So menu, nope, graph entry, scatter plot, nope, damn it, that's what gets kind of rush. Speed, I know, speed, stopping distance, enter, 0.3x minus 0.42 squared. Hey guys, look, right here. Notice, now I have a graph of the stopping distance. And look at that model once we squared it. How does it do? Not just it curves up, look at how the model does with the data. It aligns with the data, doesn't it? So guys, it is really powerful to linearize that data and then use that linear model to get a model for the original data. We're going to apply this to understand inverse functions Thursday and Friday and even after Thanksgiving break. Please be ready for that test tomorrow. You are awesome. Great learning today. I appreciate you. And Crystal has Hero Friday this Friday. What's up? No, this is not on your test, guys. It is just the polynomials on your test.
The rate of change is on there, right?